What is up? Welcome to 3.3 Electronegativity and Polarity. So, today we are going to talk about what makes a bond covalent, ionic, or polar or non-polar, right? So, if they have a slight positive charge, if they have a slight negative charge. So you can consider hydrogen gas, right? So since hydrogen gas is a covalent bond, the attraction of the electrons are the exact same. And the attraction of the electrons is called something that I'll tell you later, right? But now consider hydrogen with chlorine, right? HCl, right? So from last lesson we can deduce that HCl is actually a compound because the chlorine has 8 electrons and hydrogen has 2. So the hydrogen, the HCl has many more protons in Cl attracting the electrons. So the electron goes around Cl more than H whenever you're doing a covalent bond, right? So it's just like water, right? So we have H, and O, right? H, and O, right? There's 6 electrons around O, but there's a lot more protons around O than there is around the 2 H's. But no, there's 4 electrons around O, right? So one of these has a regular bond because of its tetrahedral shape, which we'll talk about later, and one of these has one of these, which signifies that I'm sorry, that is the wrong drawing. It has one of these, which signifies that it goes around the oxygen more than the hydrogen, right? Because the oxygen has more protons attracting the electron, right? So compounds that have more than that have one or more having more electrons than the other is called a polar bond, right? And the electrons don't have to separate, but the electrons can separate. That will make it an ionic bond, right? Right. So HCl is called a polar covalent bond because the electrons hang out on the chlorine longer than the hydrogen. So the chlorine always has a slight negative charge more than the hydrogen. There's a high probability that the electron lands on the chlorine, right? So the polar covalence is like the halfway point between the nonpolar and the completely ionic, right? The completely ionic bond, which is you transfer the electron, right? Ionic means electron transfer, but regular non-polar covalent means the electrons are shared equally. So the polarity of the bond is also known as its electronegativity, right? Electronegativity. Electronegativity, the higher the electronegativity, the more unbalanced in charge the bond is, right? So the electronegativity of a bond can determine what type of bond it is. I don't know what I was on, but determine what type of bond it is. So if you refer to this is like the electronegativities of all of the elements, right? Fluorine has the most because it has the most electrons. No, fluorine has the most because it has the most proton to electron compromise, right? Because electrons don't like being near electrons, and fluorine doesn't have many electrons, but it has many protons, right? Right? Because once you get to Cl, once you get to chlorine and bromine and iodine, there's more electrons to block the the share of electrons, right? It's a little bit confusing. I say it a little bit confusing, but we are going to calculate the polarities of this. So C and H is 2.5 and 2.1. So 2.5 minus 2.1, right? You take the difference of the electronegativities, which will give you 0.4, which classifies it as a polar covalent bond, or slightly polar covalent bond. It's not really but polar covalent, right? Okay, but if we use OH, it says D here, but this is actually O, right? So boron, carbon, nitrogen, oxygen, fluorine, right? And then neon and sodium. But okay, so we'll have 3.5 minus 2.1, which is 1.4. This is likely polar covalent. So polar covalent. This is slightly polar covalent. Hydrogen and fluorine, which is the bond that we just witnessed. That's 4.0 minus 2.1, which is 1.9. So this is polar covalent, which is it's nearly ionic, but it's not ionic yet, right? In some textbooks, it'll be 1.8, right? 1.8, and it would be ionic, but we're going to the 2.0 standard, which means it's not ionic, right? So SS is it's the same thing, so it's just 0, which means it's nonpolar covalent. Nonpolar covalent, right? Number 4. So your polarity can influence the solubility of a substance as well, right? So salt can dissolve easily in water because it's an ionic compound. So the hydrogens from the water, right? The hydrogen, it's called a hydrogen bond because the hydrogen and the oxygen bond together in the water, right? Because of the polarity of water, the hydrogens and oxygens like to bond together in water, and you get this like stuck together water pattern rather than like droplets of water rather than just dispersed amounts of water. You get droplets of water because water sticks to each other, right? So when salt goes into the mix, you have right, and this symbol right here, the symbol right here determines it's like a small delta. I think it's a small delta. I'm not sure, but it determines the charge. So this is plus and this is minus, right? Um, so when salt goes into the mix, you have our chlorine, which is negative from NaCl, right? NaCl. We have Na plus and Cl minus. So the Na gives the electron to Cl to give the ionic bond of NaCl. Na gets sodium gets attracted to the negative, it's a slight negative charge of the oxygen side, and I am sorry, this is a wrong one. Okay, so replace, so S correction, or I'm going to correct myself, right? So oxygen is actually negative and hydrogen is positive. So I'm really sorry. Hydrogen is positive, oxygen is negative. This is a wrong thing. Replace all the delta minuses with the delta plus and replace all delta plus with delta minus, right? So the chlorine actually gets attracted to the hydrogen because the chlorine is negative and the hydrogens are positive because the electrons don't go around them as often. And the sodiums are attracted to the sodiums, right? The sodiums are attracted to the oxygens. Um, and this allows them to break apart. This allows water to break these guys apart, right? If you actually calculate the polarity of water, it's about 1.4 electronegativity. So anything that's above 1.4 electronegativity, water can just break up easily, right? And salt is one of the examples, and there's probably more examples, but maybe uh, sugar can also be broken down, but sugar isn't actually. I don't think sugar is actually polar. I'm not sure though. I haven't done organic chemistry yet, but there. So if it's more polar than water, then it can easily dissolve in water because of the hydrogen bonding between water, and because of the way that water acts whenever it meets an ionic substance. So there are electronegativity trends in the periodic table as well, right? So once you go right, if you go right, it'll be more electronegative, and if you go up, it'll be more electronegative. So if you go down, it'll be less electronegative, right? Or left, right? So for example, radium or like some of these bottom elements, they are not electronegative at all because there's so many electrons and there's so many protons already that sharing of an electron is actually quite a hard task to do, right? But the atoms on the right is more electronegative because they really want to get that electron, right? As opposed to the atom on the left, they really want to give away the electron, right? So the molecules, so carbon gas, for example, or oxygen gas, or hydrogen gas, molecules like this are completely covalent. Completely covalent, right? And diatomic polar, no, diatomic ionic bonds, right? So, for example, hydrofluoride, actually not really, hydrofluoride or sodium chlorine, sodium chloride, or sulfur, I don't know, potassium sulfide, right? They're ionic, and they can break down easily in water, because they are they're ionic. They can break down easily in water because they are more ionic than water, more polar than water, and water can just break them down easily. Right. So find the electronegativity of and label the bond as nonpolar, covalent, covalent, or ionic. So we're gonna go back here. We're gonna copy this because this is what teachers do. We copy stuff, and we're gonna paste it right here. Right. So hydrogen and carbon, hydrogen and carbon at electronegativity of 0.4, which is polar covalent, right? Carbon and fluorine, electronegativity of 1.5, polar covalent. Fluorine and potassium, so potassium fluoride is 3.2, so that's ionic by a big amount. Right, sulfur and chlorine is 0.5, so it's polar covalent. P and O, phosphorus and oxygen. This is O, by the way. This is 1.4, which is polar covalent. And finally, cesium and oxygen. Cesium oxide, that's a thing. Okay, that's pretty interesting. Cesium oxide is 2.8, which means it is ionic. That's going to be it for today's lesson. I'll see you next time with molecular structure and other stuff, right? Molecular structure.